Hello everyone, I am Sunandita Patra and welcome to the demo of integrated acting, planning and learning using hierarchical operational models. So let us first understand that in what kind of domains such integration is important. So here consider like an actor trying to fetch this green ball. So the task is say pick up object and then go to some location and then put down the object. Now what can happen is that there are multiple such objects, so there can be multiple tasks so that the actor may need to consider, and there can be dynamic events such that some for example, say the actor is trying to pick up one object, say this one particular, but some emergency happens, and this location of the emergency is this yellow box, and the actor, instead of picking up the object, it needs to go immediately to the emergency and address this current emergency. Now that's like one uh, case where integration of acting and planning is important. Another case is where there are dead ends, say there is this lava, and if the actor just goes into the lava, say it steps into the lava, then it will die. So we want to avoid situations where there are dead ends. Let us see another case where the actor needs to perform some sensing actions to sense the environment, because see, the shaded gray area is the place where the actor can see that where the objects are. So here the green object is within the shaded area. However, in some cases, the object may be out of the shaded area. So the actor needs to cover the whole area, avoiding the dead ends, go to the place where the green object is, and then pick up the object. So these are like sensing actions which the actor doesn't know the outcome of. So we saw that there are different kinds of scenarios where integration of acting and planning is important. You can't just take a plan and carry out all the way through, because a lot of things could go wrong. So let us see how our tool looks like. So the main, let us look at the main interface. So there are 5 available domains that you can choose from. Say, let us choose fetch domain, and let us see that how to define the domain, like what kind of language we use. So the language is the language of hierarchical operational models. So here, first you have to declare all the tasks that the actor needs to accomplish. Say here the actor needs to search for the object, fetch the object, recharge. So if the actor, so the actor can carry like a maximum amount of charge, and as it moves in the environment, it loses the charge. So it has to recharge periodically. It can move to some location L. It can address the emergency at a location L. And for every task, this is the critical part of the knowledge representation, that there can be multiple refinement methods. So for search, there are 2 methods, method 1 and method 2. Let us look at how the methods look like. So the methods are programming procedures, which are like basically Python programs to accomplish the task. So here there are 2 methods for 3 methods for recharge. So first, in the first one, the recharge method 3, the robot R charges itself and then carries the charger, so that later in the path, if it needs the charger, it can charge there itself. Recharge method 2, it charges but does not carry the charger, leaves the charger. It may be used by other actors. Method 1, it just charges, and whichever the charger is being carried with another robot, and that robot takes the charger. So like these are basically examples that you can encode any kind of knowledge that the human expert as refinement methods. Now Let us look at the different acting engines. So there are two acting engines you may use. So the acting engine keeps track of the different tasks that the actor needs to accomplish and how far along you are in achieving that task. There can be different problems. So let's see how to define a problem file. So here, this is a problem file where you may say that, okay, each action, which is like a low level command that is performed by the execution platform, how much duration does it take, or how long it is, how long it takes to be executed or simulated, the what is the configuration of the environment, what kind of locations are there. So the locations may be different in different problems, and the connection of the locations may again be different, where the robots are located, how much charge each of the actors have, where is the position of the charger and the object. And here, this is a simple example. So there are two tasks. First one is fetch. Robot R1 has to fetch the one object we want, and the robot R1 has to address some emergency. So this is like a dynamic event that the robot needs to consider. Now, let us look at, say, the problem 36. And let us use the planner UPOM and say for the planner, a maximum limit of 10 seconds. Now, one key thing is the utility, like what is the utility function that the user wants to optimize. So depending on the domains, the utility function may be different. It may be the efficiency, which is the reciprocal of the cost. So you want higher efficiency and lower costs. It may be success ratio. So what is the probability of success when you choose a particular refinement method. And it can also be the cost effectiveness, like a combination of success ratio and retry ratio. Then you can choose the learning strategy, which is, let us choose none, but there are different possible learning strategies. Learn M is where you use some learned knowledge of past experiences to make the checks. If you're curious, you can we can discuss this during the live demo, or you can always reach out to me anytime. So for now, let's choose none and then run. So as we can see here, the tasks were emergency. So every event is considered similar to a task, because event is something you recover from and task is something that you accomplish. But in perspective of the actor, it's both are considered equally, because they have to recover from events and accomplish tasks. Now, the result of emergency is success. So in this case, the robot was able to address the emergency, but for some non-deterministic failure, or here in this case, the robot doesn't have enough charge, so it is stuck at a dead end. Now let us see what happens if we maximize the success ratio. In this case, because we want to maximize the probability of success, so both are succeeding, but the utility is higher than expected. So the utility is 0.25 for emergency and 0.045 for success for the fetch task. So utility is the reciprocal of the cost of all the actions. Now let us look at how you can define your own utility function. So to define your own utility function, you have to say that how that utility function is added or subtracted, because the way the planner plans is it uh, needs to create it needs to compute the utility of like a whole plan. So that would be the sum of the utility of each of the low level actions. So in this case, the utility uh, what you need to define a new utility function is how you compare two different utilities, and how you also check whether they're equal or not, and how to add the utilities. So if you define this, then the planner will be able to optimize the utility that you want to optimize. Thank you.